Hello, my name is Adrian Pina Sanchez. Today I will present Cosmic Math and esoteric machine learning algorithms for classification. The main idea is to train a neural network without using gradients or back propagation. Instead, we use a random bit flips that simulate cosmic radiation, acting on the model's weights. Even though it sounds absurd, that is exactly what makes it useful as a learning exercise because it helps us understand why traditional optimization methods work so well. And well, for a start, what are the esoteric algorithms? Before explaining cosmic graphs, it is helpful to us keep some context about the esoteric algorithms that are intentionally absurd, inefficient, or impractical, rather than being useful to the traditional sense. They help to explore the limits of computation and show, by contrast, why standard algorithms are well designed. There are several important families. There are some known ones, such as Bogosort, which depends entirely on chains. There are no phase-based ones that are, for example, the miracles or the miracle sort. And there are destructive ones like Stalin sword, and there are physical ones like the spaghetti sword. Our classification for cosmic graph it's mainly inspired in the faith-based algorithms category. So, the miracle sword. The direct inspiration for Cosmic Thread is Miracle Sword. The idea behind Miracle Sword is to place an array in memory, check whether it is already sorted, and if it's not, simply wait until a Cosmic Ray flips a bit in one, and the array becomes sorted by chance. Of course, this is sound very ridiculous, but it's loosely based on a real physical phenomenon known as single event offset, where high energy particles can alter bits in memory. Cosmic Black takes the same idea and moves into the machine learning. Instead of waiting in a way to become solved, we simulate that the bit flips and ask whether those random rotations can improve the weights of a neural net. So for start, how it works or algorithm. Now let me explain about how Cosmic Graph works. It is a supervised binary classifier implemented as a multi-layer perceptron, but without propagation. First, we initialize the number with random weights. Then, at each iteration, we choose one weight that's random and convert into a 32-bit IEEE 7054. And then we gonna flip a random bit that simulates the cosmic ray and evaluate the accuracy on tuning that. If the accuracy improves, we accept the mutation. If not, we reject and revert until we accept it. It repeats until the target accuracy or max iteration becomes with the number that we set. So um this slide is very important because it explains why some mutations are much safer than others. In a 32-bit uh, floating point number, there is one giant bit, 8 exponent bits, and 23 mantissa bits. If we flip a mantissa bit, the numerical value usually changes only a little, but if we flip an exponent bit, the value can change dramatically and they become none or an infinite number. So flipping the sign bit can completely reverse the weights. This means that not all the mutations are equally disruptive. The mantissa usually produces small local changes, and while the exponent often causes catastrophic jumps. So even though for Ostemic graph looks pure randoms, the floating point representation itself create an important structure in the search space. So for this, what are our hyperparameters? For the first one, the alpha, that is the target accuracy, which determines when training should stop. The second is lambda, which represents the radiation intensity, meaning how many vectors you attempt per each iteration. The third one is the beta strategy. This one is for which can either be uniform or biased toward Matisse a bit. And the fourth is the network architecture, because that determines how many weights exist and therefore how many mutable bits are able in the model. In our setup, the architecture is 2841, which gives us 65 trainable parameters or more than 200 mutations. 2000 mutations, sorry. Okay. In principle, cosmic graph can be imagined in four modes, or can be represented in four modes. The first one is what actually we use, and it's simulate mode, which can request a CPU and random number generation. The second is a physical mode, which will expose a known ECC memory to radiation and wait for a real bootload. The third one is a parallel mode, because mutation trials can be evaluated independently. And the fourth, it's completely esoteric spirit. It's a quantum mode. It's inspired by quantum Bogosort, where one imagines eliminating all the universe in which the classifier fails. Of course, for the actual experiment, we only use the first one, so we'll continue with that idea. For the complexity of or possible outputs in terms of space, cosmic grid plot is very simple. It stores the dataset and the kernel weights. So the binary complexity is O of n times d plus the W, where it's the dataset plus the current weights only. Uh, the best case that we can obtain will be if the initial random weights already classify their data correctly. So uh, in this case, it's O of n multiplied by d. And the expected output that we can obtain by his complexity, um, uh, it depends on the probability that a random mutation is beneficial, and the probability becomes smaller as the model improves. And this is the representation with P is the probability of beneficial mutation and explanation in domain. And the worst case, obviously, it's that can find the uh is effectively unbound, because the algorithm can keep proposing useless mutations forever, and we can accept any of them. So we those are the possible outputs, and we continue with the dataset and the results. For the experiment, we use the MakeMoons dataset from scikit-learn. It contains 150 samples, and we use two dimensions in it, arranged as two interval present shapes, which makes the classification problem not linear. This is useful because a simple linear model will not solve it, so the neural network actually needs to learn a non-trivial decision boundary with a 2-8-4-1 architecture, that is this architecture, and the model start about 26% of accuracy, but then continue to a final obtaining a 90% of accuracy at the end. So for this one, or strategy comparison, we compared the two bit selection strategies. The first is the uniform selection, where every bit has the same chance of being flipped, and the second is the Mantinsa strategy, where the bits are chosen more often. So both approaches reach roughly the same final accuracy, close to uh, 90%. However, the Mantinsa strategy has a higher acceptance rate. This supports the intuition we saw earlier, that small numerical changes are more likely to fail, or at least likely to break the model, than large and unstable exponent changes, because this keeps uh, more neutral or without side very change that can break the model. And then we continue with the lambda comparison. We almost finished. One of the important interesting results is that more radiation doesn't mean faster learning. At first, it might seem reasonable to think that the increase in lambda or the number of the flips per iteration should help the model to explore the search space more quickly and improve. But in practice, the opposite happens. When lambda becomes large, multiple mutations interact, and the chains of causing destructive changes rises sharply. So as a result, the acceptance rate collapse collapse the model and performs get worse. So this experiment shows that the search space is fragile and that too much randomness can completely damage the learning process. For the next one, the cosmic graph versus the propagation in this case, the Optimus results. We finally compared the cosmic graph with the standard backpropagation using the same network. Backpropagation reaches about 86% of accuracy, but in just 200 iterations instead of the 80,000 iterations that needs all the formats of the cosmic plot. So this is hilarious, but it demonstrates how different are the two models. And the real point is that backpropagation is vastly more efficient than using the because it uses the gradient information to move in a meaningful direction, while the cosmic plot relies on the blind trial and error. So for final, these plots show the frame dynamics more clear. On the left, the curve rises in a relatively quick way at the beginning, and then enters on a log plateau. That makes sense because at the start, there are many mutations that can improve the model, but later on a beneficial mutation becomes much rare. On the right, the histograms shows which types of bits appears more often among the accepted mutations. Once again, Mantissa bits dominates, which reinforce the idea that small numerical perturbations are more useful than the long directed jumps. So we keep with Mantissa instead of exponent. And for the conclusions, in conclusions, well, this may give us four main takeaways. The first one is that random bit flips really can train a neural network also in a very efficient way, but can fail. The second, not all the bits are equal, and this structure creates a strong asymmetry in how mutations affect the model. In third, the increasing the mutation intensity doesn't mean necessarily to help and can even destroy the performance. And the fourth, but the comparison with backpropagation makes one lesson very clear. The gradient information is extremely valuable, that it's the management of all the ML models for the idea of the gradients. And Cosmic Graph teaches this by inversion. By doing everything in the right way, it helps reveal why the right methods are so effective. And for finalize, we have the codes and all the plots that we use for the presentation. So thank you and uh, thank you so much for your attention. Thanks.